Okay, we're on to talk about quantum mechanics, which actually I'm excited about. Um, I find some of the heavy calculation stuff to be kind of boring. Uh, well, I gotta be careful what I say. I think it's the cool stuff. So you're gonna why does this guy get into chemistry? This is part of it. This is intro to quantum mechanics. I remind you, this is just the introduction. And question is, what door did you enter today? And I know this is usually what I do for a classroom because there's usually more than one door and there's the windows. And the idea, though, is that electrons behave very differently than what we call classical mechanics. So things like tennis balls and humans and books, they respond classically. So, like a classical person enters into one door. Well, what about an electron? How does an electron behave? Well, electrons can actually enter both doors at the same time and maybe even slink in the cracks through the windows as well. Electrons are really strange, at least to classical people like us, because they can be in many different places at once, and it's hard. We are uncertain where they're at and where they're going. So there's these kind of things. And here is a picture of Schrodinger's cat. Schrodinger. I guess like back up. Schrodinger is one of the few people I would love to have met. I went to the Nobel Museum in Sweden, in Stockholm, Sweden, and there was just something about hearing Schrodinger. He has this electrifying voice. They record all the people that win Nobel prizes, and they give this little speech, and you can listen to them in the Nobel Museum. And Schrodinger just had this kind of electrifying voice about him is the best way to describe it. And he was really cool. I mean, in general, well, he's a bit of a player too. That's a different story. But of course, there are some. I've met a few Nobel laureates, and a couple of have been awesome. Some of them have been absolute jerks, but that's a different story for a different time, I suppose. But Schrodinger's cat here, Schrodinger was so he couldn't handle it. Well, he couldn't handle it. He was looking at electrons and they behave. And the thing with electrons are it depends on how you observe them. They behave differently, and he's frustrated with this. And he said, "It's like I have a cat in a box, and that the cat, if I open the box, the cat is either going to be living or dead, but uh, the cat only becomes that after as I open the box, whether or not." And he has this hammer hitting like a vial of cyanide or some other gas. It's only after I open the box do I find out if the cat is living or dead. But what happens when the box is closed? Is the cat living or dead? It's kind of both at the same time, and that is part of the wave duality particle of both light and electrons. So what are the properties of electrons when we're not observing them? Obviously, we don't know because we're not observing them, but we have the math that suggests some very unique things. So it is kind of weird. It's kind of cool. And I remember when I was studying quantum mechanics, this was also when Harry Potter was really popular. And I remember reading Harry Potter and studying quantum mechanics. I was like, it's magic, it's magic. So I guess there's a little bit of, uh, kind of my own. It made me feel better at least. So studying the magic of chemistry and reading about the magic of Harry Potter. Okay, so let's talk about some properties of light and other radiation. So, light is part of a very broad thing called electromagnetic radiation. And what is electromagnetic radiation? It is it basically it's a wave that has it's a transverse wave that have oscillating magnetic and electronic fields. So if you see this picture, so like if you have a chalkboard, the red one is going on the plane of the chalkboard, and the blue one is perpendicular to it, so it's sticking out. So a light wave or other types of radiation has a perpendicular traveling electronic magnetic field, and the wave is a transverse wave. So transverse wave means that the displacement is perpendicular to the motion. So like an ocean wave is a transverse wave. So if you're sitting out in the ocean and a wave comes along, you move up and down, but the wave is moving perpendicular to the vertical displacement. That's a transverse wave. A longitudinal wave is that the displacement is same direction as the direction of travel. And sound is a longitudinal wave. So the pressure change is the same direction as what it's flowing at. So it's a transverse wave, and a couple of things. So the height of the wave is known as the amplitude, and the higher the amplitude means a more powerful wave and more energy. And the distance between the crests or the troughs, that is known as the wavelength. And so light, I already mentioned light is a form of radiation. So red light has a longer wavelength, violet light has a shorter wavelength, and it's drawn here in this image. And red is on top, violet is on the bottom, and the so I've drawn. There's a ship there. Which if you're in a storm, which storm is more powerful? It's the one on the bottom, of course. So later on, we'll talk about the higher frequency means higher energy. So higher frequency. Frequency is the number of times per time. So like, what is your frequency of eating meals in a day? So my frequency of consuming meals is a minimum of three, probably more like four or five kind of thing, because I have to have a snack here and there, right? So what's your frequency of doing something? What's your frequency of putting on shoes in a day? Like it depends on how many times I come enter and leave my house, I suppose, right? So it's probably like around 5 times I probably take off my shoes and put them back on in a day. That's like the number of times you do something. So what's the frequency for light? It's the number of revolutions per time. Okay, so here's just a simple thing with physics, and so I have this funny upside down y and a curvy v. Those are the lowercase Greek symbols lambda and nu. So the lambda, the y is the wavelength, the v, the nu is the frequency, and so this is just simple physics. The wavelength times the number of times that it goes, that's the speed of the wave. So that makes sense. And for light and other electromagnetic radiation, the speed of the wave is the speed of light. And the speed of light is 3 times 10 to the 8th meters per second. So that's very fast. And what is speed? Speed is distance divided by time. So that means that the speed of light there, that's 300,000 kilometers. So 3 times 10 to the 8th, that's 300,000 kilometers in 1 second. That's how far light will travel in 1 second. So that's the speed of light. That's very, very fast. Of course, if you are studying things in the cosmos, you're like, well, that's kind of slow. That's light years away. But here on Earth, at least for our purposes, speed of light is relatively quick. But who knows? Maybe in the future we'll start noticing the speed of light. Like if we go to the moon, there's a 4-second delay because it takes 2 seconds or so for the light to get to the moon and 2 seconds to get back. So if I guess we start calling people talking on the moon, it's going to be kind of strange. It's going to be a strange conversation. Okay. So that's speed there, speed of light. And let's see if you can do this. What is the wavelength if the frequency is 4.62 times 10 to the 14th inverse seconds, also known as hertz? Hertz is 1 over seconds. And a nanometer is 1 times 10 to the minus 9 meters. So let's see if you can solve this. I notice most of my students have no problem with this. The answer is 650. And the way you solve it is you take it's just the wavelength is just speed of light divided by the frequency. I put in there, and Chemistry is weird that we use this symbol. Physics uses L for wavelength and F for frequency, but chemistry we do that. I'm not sure why we do it this way. Chemistry, much of chemistry was developed by the Germans in the early 20th century, in the first half of the 20th century, at least until after World War II, when we got all the good scientists to America. Okay, so next I'm going to talk about is electromagnetic spectrum. So let me start with the lower wave, or longer wavelength, lower frequency. So if you look at this chart, we have the frequency in the top, and then we have the wavelength at the bottom. So a low frequency means long wavelength, and high frequency means short wavelength. And each of these different types of radiation do different things to interact different ways with matter. So radio waves, what radio waves do is they change the direction of the magnetic field of nuclei. So if you hit something with radio waves, it's going to change, interact with the magnetic properties of a nucleus. And we use radio waves to tell us, so we use them for communications. That radio waves, so AM radio, television, FM radio, and cell phones are actually in the microwave range. So is radar. Radar is microwave as well. So we use these to carry signals over long periods of time. And also, we use radio waves to do MRIs. And MRIs used to be called nuclear magnetic resonance imaging. And when someone says, "All right, we're going to scan you using nuclear magnetic resonance imaging," and people are like, "Nuclear? That's a horrible word. I'm not going in there." And then so what they did is they got rid of the word nuclear and just called it magnetic resonance imaging. Like, okay, I'm fine with an MRI. So as long as you drop the word nuclear, I guess. But the way an MRI, if you ever had an MRI, first of all, they're loud. You're in there and you hear this kind of ka-chunk, ka-chunk, bah, bah, ka-chunk, ka-chunk, bah, bah. What the machine's doing is it's moving magnets around. And what the magnets do is they align your hydrogen nuclei to a magnetic field and they blast you with radio waves. Then they look at the signal, the radio waves coming off. And from that, they can image where hydrogen atoms are. And by looking at the images, they slice you up into little pieces and they can construct images and they can tell the type of tissue that you have, any damage. Here is an MRI. I used to, well, I'm not sure what the MRI is now, but I had a back injury. This is my lower back. So I am, in fact, human, if you were wondering. And here is my back. And you can see here the really bright white line in the middle. That is my spinal cord. And then around that is, you can see the discs in my vertebrae. And you can see that there are some healthy white discs in the bottom two between my sacrum, L4 and L5, that I have two discs that are entering degenerative disc disease, as it's known. And especially between L4 and L5, there is a protrusion it's right here. It's going into my spinal cord. And that is not a very pleasant feeling, by the way. I have since recovered. I don't know what my back looks like now, because I mean, there's no reason to take a second picture of because MRIs are expensive. It's a waste of money. But this is what I was like when I was injured, and it was, like I said, it was not a very pleasant experience. Spinal injuries are quite painful. So, but you can see this. I mean, you don't need to be a medical doctor. If I told you, okay, this is a bone, this is a cartilage disc, and this is my spinal cord, and you can kind of say, okay, these are cool, these are not cool. There's something going on there. So you can really, I mean, as an untrained person, you can kind of say, okay, that is something going on. But of course, the trained professionals are much better at the details about things like this. So that's an MRI, and MRIs are very, very safe. So are microwaves. debate about, right? It's not really a debate. It's just you see some news articles sometimes like, do cell phones cause cancer? And the answer is no, they don't. So we'll talk about that a little bit later. But cell phones operate on microwaves. So let's talk about microwaves. So radio waves change the nuclear properties of nuclei. What do microwaves do? They make molecules rotate. They make them spin around. So the way your microwave oven works, so you put stuff in the microwave and it heats up your food. Remember, talk about temperature. Temperature is average translational kinetic energy. So microwave, so spinning when you throw something in the microwave, it makes the water molecules spin. And what happens is that as these water molecules are spinning, they're still moving around, and when they bump into each other, when they spin. So imagine if you're spinning, like if you're running around and you're spinning, and like say you're in an ice skating rink, right? So say you have one of those dancing moves where you have an ice skater, it's spinning. What happens if you run into someone who's spinning really fast? Well, usually that spinning motion is going to push you. You're like, oh, I'm moving slowly. I run into someone who's spinning, and then and then you move away a little bit with a little added momentum from running into that spinning person. Of course, a person is not spinning anymore or spinning less. You transferred that rotational energy into translational kinetic energy, and that's how a microwave oven works. You rotate the molecules, and then they collide in each other, and it turns into translational energy, which is temperature. So the temperature of the whatever you put in the microwave increases. So that's all you're doing with cell phones. You're heating up. You can heat things up. And heat, I mean, can burn you, but it's not going to cause cancer. In order for cancer to form, cancer is a specific mutation. When a cell becomes a cancer cell, there has to be a specific mutation such that the cell starts to grow abnormally. It has to change the DNA, so it has to change the coding of the cell. Specifically, has to damage the DNA and has to be repaired incorrectly, and then the cell can become a cancer cell. And uh, in order to do that, chemical bonds need to be broken. And something called the photoelectric effect, which we'll talk about later. The photoelectric effect, the microwaves just do not have enough energy to break chemical bonds. Uh, Ultraviolet, X-ray, and gamma rays, they have enough energy. Those are known as ionizing radiation. Those can and do cause cancers. But cell phones, nope, you're fine. You can use them all you want, and not going to damage you. Non-ionizing radiation is fine. You can get all the MRI scans you want. I talked to the tech who was giving me the MRI. He says, sometimes we test it on ourselves, and I've fallen asleep in there. So I've been in there hours in a day, and he works around. It's fine. Radar uses microwaves. The intensity of microwaves from radar is much greater than a cell phone, and people live and work on Navy vessels. They around airports and work in airports, being exposed to huge amounts of microwaves, much more than you get from your cell phone. Even though, I mean, I know you put a cell phone right next to your head, but people that work on Navy vessels, people that work as technicians on radar, they don't get cancer. I mean, well, they don't get cancer from the microwaves. Microwave oven was actually invented by a radar tech who had a chocolate bar in his pocket, and he was working on the radar, and his chocolate bar melted, and he was like, "What is going on here? What is this?" And it turns out that the microwaves were heating him, of course, and heating the chocolate so much so that it melted the chocolate. He's like, "Hey, I can use this to cook things now." So that's how the microwave oven was invented. Okay, so moving on. So microwaves, now we go to infrared. What does infrared do? Infrared makes molecules vibrate. So you can do some electronic transitions with infrared, but in general, it makes things vibrate. So it makes molecules dance, if you will. Then we get to visible light, and this is the light that we can see, of course, hence the word visible. And what visible light does is it does electronic transitions. So Electrons absorb energy in the visible light range, and it can promote. And as electrons go down, it emits light. We'll talk about this later on in the chapter. And here is the visible spectrum. It's visible light is considered between 700 nanometers and 400 nanometers in length. Although most humans can see down to about 800 nanometers. 800 nanometers to me looks like a really dark brick red, is the best way to describe it. And some humans can see beyond violet. I can see at about 380 nanometers, and 380 nanometers looks like a really light, kind of a lavender kind of color, like a lilac lavender color to me. And some people also have had their corneas removed. I mean, now when we have cataracts, we can put in lenses, but in the old school way, it is removing the corneas. And some people can have reported seeing further into the ultraviolet because of that. And one of them is actually was the painter Pierre Auguste Renoir, the the French impressionist. He had cataract surgery, and some of the colors of his paintings had changed, and it's been hypothesized that he started seeing in the ultraviolet, and that's the reason why some of his paintings had changed. So, and some people can just naturally see in the ultraviolet. It's I mean, like I said, I can, but I'm not very far. Some people can see it much further into the ultraviolet than I can. And But also look at some of these names. So ultraviolet means beyond violet, and infrared means less than red. So infrared, less than red, ultraviolet, beyond violet. And red has low energy versus violet has high energy. And we as humans, we this is kind of how our eyes work. We have so I'm trying to the y-axis is intensity, the x-axis is the wavelength, and we have two different types of cells in our eyes that can tell colors. We have or tell light. We have rods and cones. Rods only work by intensity of light, and they don't need as much signal to work. And cones tell colors, but they need more intensity in light. We have most humans, I should say, most humans have three different types of cones, and we can see red, green, and blue. Of the colors, we see green the best. And ironically, it is also the color that is the highest intensity from the sun. So the sun's peak output is a sort of a lime green color. Like if you ever seen like with those fluorescent green shirts that people wear like laborers wear them, and they paint fire trucks that color now. You're like, wow, it's a bright color. It's because our eyes see it the best. It's our most intensity color. So we see green the best, and it's the same color. That's the maximum output from the sun. So the sun's actually a green star, if you will. That's I know we call it yellow, or the sun looks white to me. But if we were really good spectrometers, and we'd say, wow, the sun's got a kind of a greenish color to it. So that's our green sun. And an interesting feature about us humans is that our red signal has an absorption in the blue side of things. So actually near the end with violet. And so for us humans, we have a very hard time discerning between purple and violet. Well, essentially we cannot tell the difference between purple and violet. It looks the same thing to us. What is purple? Purple is blue and red together. What is violet? Violet is a wavelength of light with a light with a wavelength of about 400 nanometers. So if you hit our eyes with a blue and a red photon at the same time, and or a violet photon, we will get the same signal to our brains, and we will not be able to discern between them. So that's that is a unfortunate thing about us as being humans. We're not spectrometers, but humans though, we compare the other animals, we see very well. So are there other animals that have other better things? Like, well, yes, raptors, like eagles, can have better resolution than we do because they need to see things like prey, like squirrels or bunny rabbits from really high up. So that's that they can see very details very well. And mantis shrimp, they have, well, we have three colors. They have many more than we do. But the difference between both eagles and mantis shrimp is that we have bigger brains, and we even have a part of our brain, our occipital lobe of our brain, geared towards interpreting the visual input. And in my opinion, I think we see of any species here on Earth, we see the best. So we can tell more information from uh, sight than other animals can. So it's like they're like cats, dogs, and well, bears especially. They're really strong sense of smell, and their world must be incredibly complex when it comes to smelling something. They couldn't. So the same, where they have the smell, we humans, we have the sight. We do that. Well, okay, and then think of a color like orange. So orange is probably like right here. Our brains interpret the signal, the relative strength of those three signals for most people. Some people have less than three. There's a couple people that have four. They're known as tetrachromes. So they can, but being a tetrachrome is not that big of a deal though, because our brains are geared toward dealing with three. So a tetrachrome is not a very big advantage uh, to a normal trichromatic person. So, but it's kind of interesting. So, but I mean, we humans, we use our sight, kind of like, oh, is that edible? Is it a danger? Is this what is, it's kind of, we're very reactive to it. And okay, but let's move on. Talk about visible light. So, what do we learn about radiation so far? Radio waves change the nuclear moments of nuclei. Microwaves make molecules rotate. Infrared makes molecules vibrate. Visible deals with electrons. Then ultraviolet, what do ultraviolets do? They deal with big electronic transitions, and or they can rip electrons off. So this is known as ionizing radiation. Ultraviolet light can rip off electrons on the surface, like on the valence, the outside electrons. And ultraviolet light can and does cause cancer. What type of cancer? Specifically, skin cancer. Right? The ultraviolet light does not penetrate very far beyond the skin, and then move on to X-rays. X-rays are higher energy. X-rays can go down to your core, so the core of the electron. So it causes electron transitions and rips electrons off deeper in the atom, and that's the X-ray, and has higher energy. So you cannot use ultraviolet light to take an X-ray. Like you can't image your bones, but you can use an X-ray to image bones. X-rays can cause skin cancer, but they can also cause worse cancers like bone cancer. So it's not, ultraviolet light is limited to its penetrating power and can only get beyond the skin. X-rays can cause other damage all the way through. And then gamma rays. Gamma rays deal with nucleus. Just like electrons go up and down energy, protons and neutrons also go up and down in energy. And the energy differences and transitions are resulting in gamma rays. And gamma rays can ionize anything. They're very high energy. So those are definitely dangerous. So there we go, from low to high, and that's what they do. And I am a spectroscopist. I used visible light. Oh, I use infrared and visible. I use lasers. What is light? The contemporary definition is infrared through ultraviolet. We call light. So infrared light, visible light, ultraviolet light. We do not consider microwaves to be light. We do not consider X-rays to be light. But contemporary science calls that. It used to be light was just visible light, but now I guess we're a little more inclusive now in our definition of light. It's funny how there's almost like generational changes in terminology and science. Okay, so some more. Let's talk about wave-like behaviors. So Waves in phase cause constructive interference, and waves out of phase. So that what I mean is the amplitudes. If you notice here, the amplitudes are exact. And what happens when you have one wavelength of one amplitude with one wavelength? What happens? You make a big wavelength of a bigger amplitude. So that's what the constructive interference is. And there's destructive interference when they're out of phase. And so it's like if you have these two waves and they're out of phase, what happens? Nothing. They cancel out and destroy each other. And what's fun you can do if you live near a lake or something where the water is still, start throwing rocks in the lake to see what happens. You'll see constructive and destructive interference patterns arise from that. And another thing, so this is going to be important when we talk about wave particle duality. So let's say that you have a bunch of, so right here, pretend like there's an ocean wall. So here's an ocean wall, and here's a bunch of waves coming towards a crash against this wall, and there's a hole in the wall. What happens is the waves will kind of go through in this diffracted wave pattern. So that is a wave-like behavior. So this is different than particles. Say that you are you have a machine gun. So here's your machine gun, and you're shooting a bunch of bullets at a wall, and there's a hole in the wall. What happens? Well, most of the bullets get stuck by the wall, and where the opening, the bullets can go through. That is a particle behavior. So waves and particles behave differently. So that's wave-like behavior, particle-like behavior. And why am I talking about this? Because electrons and photons can have both particle-like and wave-like behavior. This is more for electrons. So uh, here is a light source. So this is known as the two-slit experiment. So instead of here's my machine gun wielding person. Let's if you look at this, if you have two light wave, like if you have a light source and you shoot it towards two slits, what happens is the light waves diffract and you get a pattern. And I'm trying to show you this blue line here, that you get a peak. You get a peak in the center here. So it kind of, oh, oops. So kind of nothing there, nothing there, whoop, nothing. Oh, I had meant to there, nothing there, nothing there, like that. That's what's going on with this. So that's the interesting thing with a wave-like behavior with the two-slit experiments. Okay, and then what about light? I said light acts like a wave, acts like a particle. So this is the photoelectric effect. So this is what Albert Einstein got his Nobel Prize for. People think, oh, general relativity is what got his Nobel Prize. No, actually, relativity at the time was very controversial and not, I guess not so much, but people were very bitter about it. The German Jew that displaced Isaac Newton, if he won the Nobel Prize in that would have been very, very bad press. It would have been very provocative. It was very provocative at the time, and but of course we in the United States, we loved him. We loved Einstein. We still do. But anyways, Einstein, he used the photoelectric effect, where he discovering the photoelectric effect. Now, what the photoelectric effect is, and I'm using different colors. From left, you have red, then yellow, then green, then blue. And looking at this, it doesn't usually use ultraviolet to do this, but we can't see ultraviolet, so I'm illustrating it with light that we can see. If you hit a metal surface with a less energetic photon, nothing happens. Then you get to a certain point, which I denote in the middle with the green. And then electrons start flying off. I'm showing you the black. The electrons are flying off with a certain amount of kinetic energy. Then what happens if you increase the frequency, lower the wavelength? What happens? Well, electrons start coming up, but they're going faster. So what happens if you increase the intensity of the light? More electrons come off with the same speed. So, or velocity, I should say. So, and what Einstein said, okay, this is the photoelectric effect, and what's going on is that the kinetic energy of the electrons is equal to the energy of the photon minus however much energy that the electron is bound. And this was a big deal because we were starting to argue about quantum mechanics, and this classical mechanics versus quantum mechanics. Are things a continuum, or are things exist in tiny packets of existence? And what this did is it proved that photons existed only that light was made of photons, and then it was made of these tiny packets of energy. So light is like a particle because it exists like these little tiny packets of energy, and there's a whole set number of them. So kind of like you have to use a branch called discrete mathematics, and discrete mathematics deals with numbers only, not with continuous mathematics. Like if you continuous mathematics, like if you look at y equals x squared, for instance, you have a parabola, and between the numbers 1 and 2, there's 1.1, there's 1.00001, 1.0000035, right? So you can have an infinite number of points between just two numbers using continuous mathematics. And it turns out that the universe does not behave this way. The universe exists only in specific places. So the space-time itself and also things that make up the universe exist in little tiny packets. So electrons, photons, you deal with numbers on these are whole numbers of things. And the proof of that is actually very simple, at least for the space-time. Space-time itself, that's Einstein's term. That's what space is, space-time. And so that, let's say that you just 2 points, like say I'm touching my iPad. I'm on the left side of my iPad. Now I'm touching my right side of the iPad, and I'm calling those 2 points. If I want to travel from those 2 points, uh, it's every time I cross, even an infinitesimal sized point, it takes time. And of course, I can get from one side of the iPad to the other, and then that shows that, okay, there is not an infinite number of points between there. There's actually a finite number. Therefore, space time itself must be quantized. There must be tiny packets of existence. Maybe you've heard of something called Zeno's paradox. Zeno's paradox is like, okay, so if I step half the distance to the wall, and I go another half to the wall, another half to the wall, I will never get to the wall because I'll get closer to the certain point. You get to the quantization of space-time, and you do in fact touch the wall. So in continuous mathematics that would be a problem, but we live in a world of quantum mechanics, and because of that, space-time has structure, atoms have structure, everything has structure. So that's we'll talk a little bit about more of that when we talk about the atom. We build up the atom, how what type of structure matter has. So and this, I mean, this makes better sense. Okay, this way of describing the universe makes better sense than classical mechanics because it yields structure. Without this quantization, you cannot have structure to things, and we do in fact have structure to things. So here's one of them. Here's the kinetic energy, and then the energy of the photon minus the binding energy. So remember when I go back to talk about microwaves and uh, cancer, that microwaves do not have enough energy to ionize, and this has been proven by the photoelectric effect. If you're having a hard time visualizing this, let's say that instead of an electron, let's say I'm holding a basketball, and if let's say I'm holding this basketball with my hands, I'm holding it really tight, and I tell my nephew like, hey, try and knock this ball out of my hand, and if he's sitting there, he's punching the basketball. I'm like, ha ha ha, you can't do that. And let's say, what if my nephew goes and then grabs a sledgehammer and then swigs the sledgehammer and knocks the ball out of my hand and say, ha ha, I broke your binding energy. That's the same thing with a photon. So if I'm holding on to the basketball and I'm taking punches, and if it's a certain point, but if I get hit hard enough, that ball's gonna be flying out of my hands. And what is the speed of the basketball flying out of my hands? It's gonna be the energy of the punch minus how strongly I'm holding the basketball. And that is exactly what's going on here with the photoelectric effect. Same idea. Oh, and then the one of the equations that have come from this, energy is equal to H times nu, the frequency. So H is Planck's constant. I'm sorry, yeah, Planck's constant. 6.626 times 10 to the minus 34 joules per second. So that's going to be an important constant as we're doing these calculations. So let's do one here. A nitrogen gas laser pulse with a wavelength of 337 nanometers contains 3.83 millijoules of energy. How many photons does it contain? So, in doing this, let's look at this. So to give you an idea how we're going to solve this problem, let's say I have $20, and if I have $20, how many $1 ice cream cones can I buy? So if I have $20, how many ice cream cones can I buy? Well, I take my principal over the price, and I get a number. In this case, it's 20 over 1 is 20 ice cream cones, right? So how do I figure out how many photons I have? Well, same idea of the principal over the price. I take the energy divided by the the energy per photon. Then from that, I'll get the number of photons. So that means I need to take 3.83 times 10 to the minus 3 joules, which is that, divided by the energy per photon. And the energy per photon, this is equal to h nu or hc over lambda. And that's just the hc over lambda, that's just because of the speed of light. The lambda nu is equal to the speed of light. Oh, I dropped my book. Okay. So let's do this all at once. So we have 3.83 times 10 to the minus 3 joules all over h, 6.626 times 10 to the minus 34 in joules times seconds. Speed of light is 3.8 times 10, oh no, geez. 3.0 times 10 to the 8 meters per second. And wavelength is 337 times 10 to the minus 9 meters. So look at the units. Joules cancel, times second, divided by second, meters. Okay, and doing that, throwing in our calculator, we get 6.49 times 10 to the 15. So just like atoms, you're like, that's a lot of photons, just when we're doing moles. So we had 10 to the 23rd. Oh, that's 23rd is higher than 15, but still, that's a lot of photons. So photons are tiny. There's not a lot of energy in photons. But if you get a lot of them, they do pack a punch. Okay, so let's see if you can follow this one. Laser pulse at 532 nanometers has a pulse at 4.67 millijoules. How many photons is this? So I want to try this out. And answer is the first one there. Okay. Wait, are we done with this section? I guess so. All right. I will see you for the second part.